In this video, we are going to talk about big, complex motherboard and digital board design. And Istvan is going to talk about this topic. He has been designing this kind of very complex boards, motherboards and server boards for over 10 years. So I'm really curious what we are going to learn today. And it's going to be from overall, so we will talk a little bit about the blocks and what is inside of these big boards, but we will go also into, we will be more specific, we will go into electronics, about the chips, interfaces, and yeah, that's what we are going to talk about. Is one correct?
Yes.
Okay, so let's start. What does it mean, complex design?
So I have a slide about here showing 4 different photographs of different kinds of boards. Complexity refers to how many components are on a board, how big the board is, and how much effort it takes to design it. So most people are familiar with microcontroller boards. They have about 50 components. One guy can do all the design for it in like a few days, probably. And then there are larger ARM CPU-based boards. You can find these in your phone, in the TV boxes, and other places. It would take a few weeks to design it instead of a few days, tens of thousands of dollars cost, and then you would need separate firmware engineers. They have a lot of firmware to develop for these. Then the main topic is the computer motherboards. These are even more complex than ARM-based boards. It can take a year to develop it and hundreds of thousands of dollars.
I would interrupt you here because I receive many questions from people like, after I watch your courses or after I watch a video, can I design a motherboard or can I design my smartphone or something? So what you can tell them about this?
So the very first of the microcontroller is what you can design at home. If you want to spend more than you spend on your car to design an ARM-based CPU board, you could do that at home, but it's typically not done at home, but already at a company with the staff, engineering staff, manufacturing engineers, sales, and all kinds of people are needed to get a product like this together. And for a x86 motherboard, it grows to so big that you need a lot of people to work on it. Even though one person will design a schematic, there are several other people who have to work on it. And I don't think people have that in their garage hiding under the desks, a dozen people with engineering diplomas to do all kinds of activities on it. So this can only be done at a corporate hardware team. I guess the smallest arrangement for designing a motherboard would be a small company, but small companies rarely do motherboard designs. Let's say a small company with at least 50 employees might try to implement something like this, but it's not very common.
And we will, a little bit later, we will explain why we need more people, but to be more specific, for example, at least you will need someone who can help you with customizing BIOS, or there may be also microcontroller which need special firmware. So it's not only like one guy who can design schematic and maybe do also PCB layout, but there is a lot of software which is behind designing this board. And so what about the server boards? You have some examples. Can you show on camera how big these boards are?
So first, I cannot show the boards that I designed, but I can show boards that are similar to my designs, and I bought them on eBay for demonstration like this. So this is a server motherboard made by Supermicro.
Can you put it even a little bit up? Yeah, okay.
Like this? Okay, so it has 2 processors on it, here and here. It has obviously the chipset, that is a South Bridge. What else? Ethernet controller. There is also somewhere some glue logic CPLD and a management controller. There is an optical port that is not put on it. Okay, like this.
What other boards do you have on your table?
Okay. I have a laptop motherboard. It's from my old laptop. It's much smaller and simpler. I think it has about 1,200 components maybe, but a server motherboard probably has around 5,000. So a larger processor needs more voltage regulators, needs more phases of the voltage regulators, needs more clock signals, a lot more supporting circuits are needed on the higher performance board design. That's why they are larger. This is obviously a processor, a memory, and this interesting thing here is a management controller. So that's a microcontroller. When people design a microcontroller board at home, they might do some simple application on it, like a reader, sensor, or something. These microcontrollers are the same kind of microcontrollers, but they are used as a subsystem in a larger design, and the firmware for it is more complicated. So you would need a firmware engineer to write the program for it for several weeks or months just to have have the program on it. But there's a BIOS flash chip that needs a BIOS engineer to develop that. There might be device drivers to be developed. So the more complex the board, more software it needs, and the software team grows.
And we will talk about these blocks a little bit later. You have like more details about. Show the biggest one, the biggest board. What you have there.
Okay, so this is the same as on the slide. This is a card that was used in a 4G base station, cell tower, in a cell tower. This has, this would be reverse engineering to explain what is on it, but I think it has 3 processors and several bridge chips and other complex devices on it. I would assume this has about maybe 7,000 components on it, and probably at least a dozen or 2 firmware engineers working on it. It wouldn't be surprising to find out that maybe 100, 200 firmware engineers have to work on it, on this one project.
Wow.
So in some cases that happens.
So and you worked also on this kind of designs, or
most of my designs were this kind. And all my designs were embedded or industrial data center types. I didn't really work on consumer electronics. They have their own aspects. For example, everything has to be the cheapest and the simplest, while in industrial designs, the cost is still one of the aspects for design, but not that much, not as much as consumer. For example, it might cost $10,000 to manufacture a board like this that I showed, while a desktop motherboard has to be manufactured for like $100. It's not $10,000. So the different cost target is used, different kind of components. Embedded boards also have components that the desktop motherboards don't have or don't need, because all these embedded boards are custom for some application. There are components that are only used in those. Those are expensive components. It might cost, a bridge chip might cost more than a processor or the desktop PC.
Okay, let's move to the next slide. So we are going to be a little bit more specific. I get many questions about x86 boards or these complex boards. People would like to know a little bit more how it is different from standard boards. So why designing this kind of boards is different?
x86 processors, and they come with a chipset. So they usually have 2 chips, 2 complex chips on a board. They have to process a lot of data with the measurable performance. So because of that, they also consume a lot of power. They also have high-speed interfaces to memory and to these expansion cards that also increases the power and performance of the device, both the processor and the chipset. They need a lot of supporting circuits because these processors and chipsets are specialized for the performance, to provide the performance. So a lot of other things have to be provided to them from external chips on the motherboard, like clock chips, voltage regulators, Ethernet PHY chips, Super I/O chip, audio codec chip. In case of a microcontroller, all of this might be in a single chip. But in a motherboard, it spreads out to separate chips.
So let's be a little bit more specific. So processor is basically only processor. Or sometimes I think there is also memory interface. So because it needs like the fastest access to memory. But otherwise, only the other interface is connection between the processor and the chipset, correct? Or
so the processor has the main interfaces to its memory. It takes up at least half the pins on the processor. Then a high-speed interface to the chipset. And there is usually a wide PCI Express interface that is used for some of these expansion slots.
And then, so why do we need chipset? What is on the chipset? And why it has to be separated chip?
So the chipset has all kinds of slower interfaces like SATA for the hard drives, I2C interfaces for the sensors, SPI interface for the boot flash, ARPC interface is a 33 megahertz synchronous interface for the Super I/O. The Super I/O is a separate chip and it provides serial port or keyboard and mouse port. It has a slow interface to the AD converter. Now, the chipset, because of the slow interfaces and because there's so many different types of interfaces and because of the power management logic in it, is designed a different kind of silicon process than a processor. The processor probably the latest, I don't know what it is now, 3 nanometer or 7 nanometer, while these chipsets are designed probably a lot earlier technologies, probably 60 nanometer or something like that.
And I remember there may be different architectures. I remember so when I was starting with x86 design, then it was processor, North bridge, and South bridge. Or for laptops or notebooks, it may be there may be a little bit more integrations. Or how does it work? Are there differences?
So I remember designing motherboards with CPU North bridge and South bridge, but I think the last time they had this configuration was around 2010, 2011. After that, they started integrating the North bridge and the South bridge on the same chip. Now there are a few processors where all of it is integrated in one. Like this laptop motherboard I showed, it just has a Intel Pentium Silver processor. It is actually South bridge, North bridge, a CPU, as well as a clock chip all in one. But the higher performance ones, like the desktop and a server, they still have a South bridge and a CPU. So we don't design anything with North bridges anymore. But what a North bridge used to do was that the memory interface came out of the North bridge instead of the CPU. And the graphics was also in the North bridge or interfacing the North bridge.
Okay. Now, I think in the next slides, you have a little bit more about the other differences. For example, one of the differences is power sequencing. Can we jump to a slide where you have power sequences for this kind of boards? So first, maybe let's talk a little bit about powers. Why?
Power
management.
Yes, so there is a power subsystem. So actually, a design starts with a top-level block diagram that shows the main processing devices and the IOs. Then we go down to create more block diagrams for the different subsystems. And then there are subsystems for example, for power, clocking, and thermal sensors subsystem. In case of the power subsystem, this is a generic one, an image from my book. It's not specifically a desktop motherboard. It's more like an embedded with. It could have CPUs and FPGAs on it. Each of these large main devices have several voltage regulators directly feeding that one device. Now, in a motherboard, you have two main devices, really one main device, and another one is also considered a main device. But in these embedded boards like this, you have, I think this one has 6 main devices. Each of them has like a half dozen voltage regulators. These are not shared with the other devices, even if it's the same voltage. Instead, they just have it right next to the processor or FPGA and just feeding it with a short and wide power plane. So a board ends up with dozens of separate voltage regulators.
So it's not like, for example, 5 regulators on standard small board, but there are many, many regulators. So power management in this kind of complex boards, it can be really complicated.
Yes, so there's something called the power on sequence. You cannot turn on all of these at once. Instead, you turn on one, wait for it to complete its turn ons, then you turn on the next one and the next one until all of them are done. That is done by a power sequencing chip, either a power sequencing chip, a small FPGA, or a management controller, depending on what kind of product it is. On a computer motherboard is typically a management controller. That's a microcontroller that has a power enable and power good digital signal connecting to each of the voltage regulators separately. If you have 10 voltage regulators, there's 10 enables and 10 power good signals. So the power sequencer, whether it be a FPGA or microcontroller, will wait for the power good signal of the, so first turns on the very first rail with the enable, and then wait for its power good signal to go up, and it senses it through its digital inputs or sometimes analog inputs, depending on the design. And then it enables the next voltage regulator through an enable signal.
Mm-hmm. And I would like to point out, I forgot what I wanted to say. It's not only about, yeah, it is power sequencing.
So this is what a sequence looks like.
I remembered what I wanted to point out. There is not only one power stage. I think, yeah, that's what we can see here. So what makes, for example, x86 very different from other kind of boards are all the kind of power states. Can we talk a little bit about this?
Yes, so in the previous slide, it's meant for a management controller, but x86 chipsets like to be involved in their own power on and power off sequences and sleep states. So they have these glue logic signals, usually 3.0 CMOS signals that are listed here, but there are more, but these are the main ones. So when you want to when a user wants to turn on a computer, then they will. So in a desktop computer, you would have a power button, an actual button on the chassis that will go into the chipset. In a case of embedded systems, there is no user. Typically, there's automated. So a microcontroller or a glue logic will assert the same signal that would otherwise come from a button to the chipset. Then the chipset will respond with a command to turn on everything. That's the SLP-S3 signal comes out of the chipset. Oh, I forgot to point out that there's a standby rail in every computer. FPGA boards, ASIC boards may or may not have a standby rail, but x86 will always have a standby rail. It's always on.
Mm-hmm. It means when, for example, when people connect a computer to main,
yes,
then computer is already powered, but yes, it's not switched on. So that's the standby.
Yeah, so the standby rail, like a 3.3 volt standby, turns on immediately when you plug it in. And then let's say 10 minutes later, you press the power button, then this sequence happens that the signal is asserted and SRP-S3 asserted, then that tells the sequencer chip or microcontroller to turn on each of the voltage rails, as I explained before with the enable and the power good signals. And once all of them are on, the glue logic will tell the chipset that all of them are on through these. Actually, sometimes they have 2 or 3 power OK signals going to the chipset. When that is, the chipset receives that, then it will know that it can start a boot process, start reading flash memory for the BIOS, and after that it starts reading the operating system from an SSD chip or an SSD module.
Mm-hmm. And I think I would point out again for everyone who is more interested to learn about this power sequencing, these power states, they have their own names. They are usually called like S0, S3, S5 stages. And for example, one of the stages is when your computer, when laptop goes to sleep. So for example, everything is powered down except processor and memories. They are still powered, and there are even more power stages. I wouldn't go too much into details, but I wanted to explain that it's like super complicated on x86 board. This is one of the like very big differences between designing x86 and like standard smaller boards.
And not just smaller boards, even FPGA boards and ASIC boards have less power states. They might just have a standby and an on state, while x86 has standby on, mechanical off, sleep, save to disk. I think these are the states that it has. I don't have an image here. I could find one that shows a flowchart of how it transitions between different states. It's very complicated.
You have something in your book?
Yes, so I'm showing pictures from my book.
Mm-hmm.
And I have a folder with all the pictures. I'm trying to find that one.
We will talk
That,
about your
yeah,
book a little bit later. So if someone would like to learn more about what we are talking today, then actually you have a lot of information in your book. Yeah.
yeah, this is the book. We might talk about it later as well. All these pictures came from this. They were prepared for the book. So on the screen we have
Oh
this
yeah, this
diagram
is
I
exactly what
prepared.
I meant. Yeah.
The red ones are the actual states. This fully on is the same, fully on here and here. Standby state, mechanical off, S3 sleep state. And there are a lot of activities that involves power sequencer chips, voltage regulator chips, microcontroller, GPIO signals, BIOS firmware calls, software and driver calls, operating system calls that are all involved in transitioning, for example, from a standby state to a fully on state or to a sleep state.
Okay, let's go back to our slides. So what do you have after the motherboard slide? I think you have the laptop.
So,
4, yeah. So what is difference for page number 4? What is difference between laptop and standard x86 PC motherboard?
so a laptop has to be less weight, and there is a lot of simplifications on it to achieve that. The processor itself, on this motherboard, we have a 6-watt processor. Most motherboards have a 25-watt processor. It's still
Mm-hmm.
smaller than a desktop that is typically, I would say, 50 to 100 watt. And you also can see that the desktop, you have 4 of these regular large size memory slots, but a laptop has just 1 slot.
Mm-hmm.
Some laptops have 2, but this one is a simple low power laptop, just has 1 socket, and it's not a big DIMM socket, but an SO DIMM is smaller. It also carries less capacity. On this board, I couldn't find the embedded controller, but it might be this chip. I looked it up. It's made by Asus. It's kind of a voltage regulator, but I think it also has a microcontroller in it, probably. There's no data sheet to be found because it's their custom chip. Here, there is a regular off-the-shelf management controller chip, which is a microcontroller. This turns on all the voltage rails, monitors the CPU temperature, and so on. Now, in
Okay.
the laptop, you can see all these connectors. So these are external connectors. These are low profile ones. There are lots of these flat cable connectors that you don't find on the desktop. There are a lot of things in a laptop, for example, a keyboard built in, a display built in, and a battery pack, all of them connected these really small connectors. These are very low weight, like 1 gram or something. They help reducing the laptop's weight because the laptop has to be carried by a human and has to be just a few pounds, while a desktop can be really big and heavy.
Again, I would like to point out something. So we talk about power, but what is also very important, especially for laptop, is also thermal management, and that's something again not only for laptop, even for big PCs, because of how many hundreds of watts goes into processor. So again, something very different from designing smaller boards. Thermal management is very important. Can we talk a little bit about this?
Yes, I think I have a diagram that shows this one here. Maybe I don't know, it's transparent. So thermal management involves the microcontroller on the board sensing the CPU temperature through various interfaces. In case of Intel, it's the PASI interface that reads out the temperature from the CPU.
Directly from the silicon.
From the CPU. It also contains a thermal diode. I don't think it's available in x86. In FPGA and ASIC boards, a thermal diode is accessible in 2 pins. It's a basic diode with no digital logic to it. In case of Intel, the sensor and the digital logic that reads out the diode are included inside the processor, and then the chipset and the microcontroller both can read out the actual core temperature. Now, in these electronics like computers, the main processing chip die is a lot hotter than anything else in that box. So that's the focus for the thermal management, not to keep the whole computer cool, but keep the CPU die cool. So that's why they are measuring it constantly. And some computers, like a desktop or some of the laptops, have a built-in fan that can be turned on and off, or its speed can be controlled. And it's the microcontroller, embedded controller, that controls the speed. The CPU doesn't control its own speed, but rather this secondary little microcontroller does. If the CPU die is too hot, then the microcontroller will tell the fan to increase the speed. Now, this laptop motherboard I showed has a 6-watt processor. It doesn't have a fan, so it has passive cooling. So this control is not there, but there are other controls available still in a motherboard. For example, thermal throttling. You can throttle the memory bandwidth. For example, you're running an application like a game or something. It pulls a certain amount of data from the memory. The throttling reduces how much memory can pass, how much data can pass through the memory, and that will cool the CPU as well. And then
that's why sometimes maybe your laptop can be laggy because maybe its CPU is going too hot, or
yeah, so that's definitely the throttling. So the memory interface, the CPU core, the graphics processor, all can be throttled. It doesn't mean that it's breaking. It's just intentionally throttled by the firmware inside. And there are thermal protections as well in all the complex electronics. Specifically for x86, there are these two signals, the proc hot and the term trip. They're coming out of the CPU. One of them signifies that it's time to increase the fan speed because it's getting hot here. But the other one, it signifies that it's so hot that you have to shut down the motherboard immediately. If I don't remember which one is which, but the second one, with that asserts the microcontroller just sequences down all the voltage regulators, regardless of what the user was running. Because this is not supposed to happen in normal operation, but if it happens, then you have to shut it down, otherwise it will just burn up and burn down your house. So it's like a safety feature.
Yeah.
So one of them is a safety feature, the other one is for fan control. That happens more often.
And when we are on this page, I see this I2C. So again, something very different. I remember from designing x86 boards is like how many I2C buses are there. Like usually when you are designing like microcontroller board, there is like one, maybe two I2C buses. But can we talk about this a little bit?
So there are some dedicated I2C buses. So the master for the I2C buses is the chipset. And the software runs on a CPU, not on a chipset. So the CPU reads the I2C devices through the chipset and the I2C bus. There are several dedicated ones and some generic I2C buses all coming out of the chipset. One dedicated one is going to the memory module that is used during power up. The BIOS software will read out. So on the memory module, there's a small EEPROM that contains information about what kind of memory module it is. Because there are different ones, different sizes. Some of them have 8-bit chips, some of them have 16-bit chips. This is read out by the BIOS through that I2C bus. And then the BIOS sets up the memory interface accordingly so it can work with that. It's automatic to the user, but the BIOS engineers have to work on this to make it happen. The memory module makers have to program the correct data in it. If we have a memory die interface that's common in embedded computers and some of the laptops, but the memory chips are soldered down, then there is no EEPROM to read out this information. So that data has to be hard-coded in the BIOS firmware, and there is no I2C transaction associated with it. There are other I2C buses used sometimes to talk to the microcontroller for BIOS update, for example. There are sensors that can be read. Some of the voltage regulators provide telemetry that tells the exact voltage, how much current is being pulled, what the temperature of the voltage regulator is. So that can be read out through I2C bus from the so-called smart voltage regulators. Not all voltage regulators are smart. Most of them are just analog components, but some of them have a digital I2C interface for reading telemetry.
Okay. We can now move to different topics. So you started with memories. Can we jump to like memory slide? Can we talk a little bit about memory layout or memory design? Because I know many hardware design engineers are watching this video. So is it complicated?
It is one of the most complicated parts of a computer. In a desktop or a laptop computer, we have 64 or 75-bit wide memory interfaces, and we have more than one memory interface in most of the cases. In embed, so these typically a desktop and laptop, there is a memory socket. It's a large, long connector. In here, it's this long connector. We plug in a memory module into it. So in a schematic, it just appears like a large component with about 200 pins on it. But the other option that is more common in embedded and in some laptops is called the memory down, when the memory chips are soldered down on a motherboard and there's no socket. This is sometimes used because it is a lower weight and smaller board area. In embedded applications, usually there's a higher density in the desktop, so that you have to put more features on a smaller board area. So the cost of having a memory down is that it requires more layers than routing to a socketed memory.
And
So we have
yeah, go ahead.
so memory interfaces have complications both in the schematic side and the layout side. In the schematic side, you have to connect the right number of address bits, chip selects. If you have multiple memory chips, even if you have multiple sockets, you have to connect the chip select to one socket, another chip select to another socket, and you have to look up each of these many signals, what to connect to which socket, and it gets us a little bit more complicated with memory down as well.
In your book, do you explain about these memory interfaces, how to connect them, and
Yes, in one section I explain about the functionality through schematic example, and in another section about layouts I explain how they are routed. The routing is complicated on the PCB layout because they are phase length control. This is a phase length control interface. If you have a socket, then it is a point-to-point usually, but still you have to have trace length tuned in groups. You have to set up complex constraints in the PCB layout tool, the constraint manager. Every lane, every data byte lane has to be matched with their strobe. The address control bus has to be matched together with the clock. But in a memory down, it gets even more complicated because you have to set up pin pair objects in the constraint manager because one signal might go to multiple chips, and you have to control the trace length from the processor to this chip, the processor to this chip.
I think you have slide for this.
Yes, trying to find it here.
Yeah.
So that comes from timing analysis. Now, most motherboard designers don't do timing analysis on the memory interface at least, but whoever wrote the processor design guide at the processor company, they did a lot of timing analysis and they determined the trace length constraints. And this is how it works. This diagram shows, it's a simplified version of a memory down interface. It only shows two memory chips and an address bus that is connected to both memory chips from the CPU, but we have to control the signal arrival time from the CPU to the memory chip or from the CPU to the other memory chip. You see there are three chips on the same net. The trace length, how you understand the trace length is not trivial. That's why they created a pin pair object. So from this pin to this pin, there's a measurable trace length. But from this same pin to this other pin, there's a different trace length measured on the same board. And that has to be controlled in the layout tool. And this is calculated by someone.
So I would like to point out, so if someone never designed this kind of length matching, then maybe they never realized that in these PCB tools, very often you can only see the total length of the trace. But in the advanced tools for layout, you actually need to set up these pin-to-pin lengths, and these tools will calculate exactly the length of the track only between these specific pins. They will not include whole length of the whole track, and that's what is important.
And this also has to be set up as a pin pair object. Now, Cadence Allegro had this feature for at least 20 years, Altium had a newer feature around 2018 implementing this.
Yeah, they have X signals, I think it's called.
X signal, yes.
But I think
Kite,
it was still not perfect. They are moving ahead with some new constraint manager or something.
yeah, a few months ago, they implemented a constraint manager
Yeah.
where you can set up all these traces in a spreadsheet. You will have hundreds of traces, and each trace would have multiple devices. Then even more hundreds of objects have to be set for trace length so that it handles the spreadsheet called the constraint manager. Now, KiCad today doesn't have a constraint manager. A lot of people try to design boards with KiCad, but for designing a PC motherboard, you would have to find some kind of a workaround to it. I don't even know how that would work.
Mm-hmm.
KiCad is typically used for ARM processor-based boards or simpler boards, but it's really complex hardware. You need a professional software, and it costs a lot of money as well. I think it's like $10,000 a year for a license.
Mm-hmm. And again, I would like to say it's not only about the total length. Many of these lengths are relative to clock or relative to some other groups of signals. So it's not so easy to actually set up these kind of rules.
Yes, and we have to know what has to be matched to what. And design guides would help with that. And also my book helps with it in a generic way. It's vendor independent. But when we design a motherboard, we usually get a lot of documents from the processor vendor. So regardless of what we learned before, we should read the processor vendor's datasheet and design guide or any other application notes that they provide. Some of them will give a very good guidance on the trace length, so we don't have to do our own timing analysis.
Yeah, I have very good experience with Intel documentation. I learn a lot from Intel design guides actually about how to design motherboard. So the biggest problem with these design guides is you need to have NDA with Intel, so you have access to these documents. And I think people who just would like to learn how this is done, it's very hard for them to get these kind of documents and read about this.
Yeah.
That's when your book may be useful.
Yeah, my book is not vendor specific or not device specific, so it it can if you read design guides from different vendors, you will find some patterns that are similar from multiple vendors. Then that's what I did, and I wrote it down in my book. Back to the data sheets. If someone tries to do a hobby project, they will not be able to get an NDA signed with the chip company for that. You have to have a company set up. And in some chip companies, for example, NVIDIA will not sign an NDA with you if your company is small. You have to have a large corporation so that they are willing to sign an NDA with you and give you their data sheet. I think Intel is willing to sign NDAs with companies that have 20 people in it.
Mm-hmm.
But an individual hobbyist will not have access to any NDA data sheets.
Mm-hmm. Well, what we didn't talk about is not sometimes it's not only about the trace length, but in these calculations we also need to include the length inside of the package of the chip.
Yes, so the processors and other devices, FPGAs, come in really large BGA packages. These BGA packages are a small PCB with these very thin traces in it, and a silicon die is soldered on top of it. So when we design a motherboard, we design in a packaged processor, not a processor die. And this package is similar to a PCB, has traces in it, and the traces have a length. So the processor vendor provides a spreadsheet with each pin, how much length is in the package. And the layout tool has to include that automatically when matching the trace lengths. So some of the professional tools like Allegro do include the package length.
We can move to different topic. So we covered this. Let's go back at the top. So what was the next one? Okay, so we talked about this one. So what is on this picture?
This?
Yeah, so here are differences between x86 and other kind of boards, because complex boards, they don't really have to be always x86. They can be different kind of, you mentioned FPGA or ARM boards or
ASIC boards, there are GPU boards. there are a lot of ASICs, and ASICs are not used in consumer electronics. So most viewers who are used to consumer electronics would be unaware of a lot of products that are being designed. Although most people who get into hardware engineering, I would say 99% of those engineers will design industrial or embedded or data center boards, not consumer motherboards. They will have to deal with all kinds of weird components that we get to later. Some of them are based on ASICs instead of processors, and an ASIC has some very specialized function. A processor can run any kind of application, and an ASIC is just made for one thing. On this slide, just showing an x86 and an ARM. These are not really the apple-to-apples comparisons, because this one on the left is an I/O block diagram that shows the main parts of the motherboard: memory, SSD, BIOS, Ethernet PHYs typically included. Right? For the ARM,
PCH, that's the chipset. So
yeah.
yeah.
In the case of Intel, it's called PCH. I used to call it Southbridge. And for ARM, it's always a single chip. I've never seen a dual chip ARM chipset. It's just a single chip containing the CPU core and all the interfaces that the Intel would have on a PCH. Most ARM processors don't need an SSD chip. Some of them can use an SSD chip, like this one from my book's example is AM69A processor from Texas Instruments. It's a very advanced ARM processor. It can work with an eMMC SSD chip, but most ARM processors just boot both the BIOS and the operating system from a flash memory chip. In case of ARM, they don't call it BIOS, they call it bootloader, but it's the same kind of function. So ARM-based systems are simpler than x86. x86 needs a lot of extra stuff on the motherboard, and that's why they are more complex and larger, at larger size.
And we already mentioned also different kind of formats. So and you mentioned like many people they don't design the consumer motherboards, but the industrial motherboards. So why there are so many industrial motherboards, and what does it mean? Why people have to design them?
First of all, there's a form factor that means that the standardized board shape and size. They also standardize what connectors are on it. And sometimes the form factor also means a chassis where multiple boards are plugged in. At this stage, they don't really call it motherboard, but for this presentation, we could call it. If we say they are motherboards, you could say that a chassis can have 8 motherboards, or sometimes 16 motherboards plugged into it, have several processors in it. Some of the slots will have a motherboard with a processor. Others will have a card with an FPGA on it or some other function. And these are more complex. It's just a single motherboard is made for a user to run one application on it, while these embedded systems with multiple boards in it, either made to process a lot of data. By the way, most of these are not operated by a user. There's no display to them, no keyboard. Rather, they run a software that is some kind of an automation, some kind of an automated function. They're put away somewhere in a data center or in an airplane or in a car, and they run their software. They know what to do. They don't need a user to click here or click there to make it do something.
But they still can be x86 Intel i7 boards, yeah? Just they have some kind of specific format for that application.
And they often have more than one processor in a chassis.
And I would like to mention one of the reasons why these industrial PCs are important is because these standard motherboards, usually they just manufacture, as you mentioned, 1 million, and then they stop the production and they move to different version. So these industrial applications, very often they require, let's say, 10 years availability or something. So that's one of the biggest reasons why there are so many industrial PCs, correct?
Yes, and they are usually made to be very specific to a specific automated application. For example, something is made for a certain type of car or a certain type of airplane or any kind of, for example, they make a circuit board with processor and FPGA for an oscilloscope. And that's what inside the oscilloscope.
Yeah.
Even though you measure your circuit board with an oscilloscope, there is still a circuit board inside the oscilloscope. And they are a very specific application. And also there are so many specific applications. While the desktop motherboard is generic, like millions of people can use the same motherboard. The embedded ones or industrial ones are made for a specific application, and there are millions of different applications. So they need a lot of engineers to design those several different types of designs.
Mm-hmm. So I remember some of the standards are like Com Express or PC 104, or here are some, I don't know, these rec systems, or what are the other? You need to plug them inside of, it's called backplane or something? How?
Yeah, some form factors have a backplane. Others don't, but it's very common to have systems where there's a metal chassis, there's a backplane inside it, and several motherboards are plugged into them. So I could show a backplane somewhere. I think this is what a backplane looks like. It's a PCB with a bunch of connectors. Each connector, actually this might be 2 or 3 connectors in a row, another 2 or 3 connectors. Each of these connector rows will have a motherboard or some card plugged into them. So this particular one, for example, can have eight digital circuits. These 2 slots here are for power supplies. So they have a power supply plugged into the backplane, the digital boards plugged into these slots, and all this goes in a metal box.
You know what I'm thinking about is like some of these boards, they are huge, you already showed them, and then you plug them inside of this backplane, and
They're even bigger.
how difficult it has to be to actually build this kind of system, because larger and larger everything is, I think more and more important is how it is connected, because it's not only about like connecting the pins. There is going to be all the kind of influence and losses, and am I right?
Yes, so in these systems, especially the larger ones, the traces are really long and go through several connectors, and they are affected by signal integrity. I think you had several separate presentations about signal integrity, but we can mention that here as well.
Okay, let's talk about this.
So I have to find.
So why connecting? It's not only about connecting pins.
It's about providing a good quality signal at the other end. Yes, I have this slide. So in these large chassis, usually we use high-speed signals to connect one card to another, and we use lots of high-speed signals, and that's because we need to pass a lot of data through. You might need more bandwidth between 2 of those industrial cards than you have in a desktop PC. So in a desktop PC, the only bandwidth you really need is to generate image on one screen, while one of these devices might have to pass data for 100,000 users at the same time who are connecting over the internet. So they have to have a lot of bandwidth, and for that they have to use very high-speed signals. The brand new desktop motherboard, I think it has up to 16 gigabit signals in it. That's mainly for graphics or some expansion slots. Some of these industrial electronics or data center electronics are using 100 gigabit signals that are like 8 times faster, and they have lots of those. And because they are faster, it is a lot harder to make them arrive intact at the receiver. So there's always a transmitter and receiver for every signal. It's transmitted from one chip, it passes through boards and arrives at another chip. And this path that the signal takes is usually characterized through S parameters that are from microwave analog engineering. And these diagrams here in the upper right show an example of what the S parameters look like when they are displayed in a curve. There are insertion loss, return loss, crosstalk, and other parameters can be computed to analyze those paths. And the actual board designs have to be very carefully designed to make sure that these parameters will meet their requirements. The
So,
requirements
for
go from
example, the red
standard.
lines are the limits, and
Yes, there's these limits. The red lines are limits. These come from standards like IEEE or PCI-SIG and other organizations created standards that define these lines. And the blue lines are what we get out of our design when we simulate it or measure it.
So do you need to simulate this kind of big parts? Like many people, even today I was reading a post on our Discord, and someone asked, I would like to design a FPGA board and I would like to simulate everything, like from audio through AD converters, DA converters, FPGA and everything. I'm like, maybe you don't need to simulate everything. So how is it?
So you have to, for example, you might have 100 signals going to the backplane. You don't have to simulate every single one of them, but you can create one or two categories, for example, the longer and the shorter signals, or if you have two different interfaces going to the backplane, then simulate each type and just one signal on it. Now, in some cases, usually we extract several signals together, but not all of them. Like a group of signals are extracted because this way you can analyze how much crosstalk you have between them. Typically, maybe 4 or 8 signals are simulated at once.
Okay, what kind of software do you use?
So there are, I created this diagram. It's also in my book that explains that the simulation has 3 stages, really. The simulator has it. Whether they explain this in the brochure or not, they really have 3 stages. The first stage is when the PCB layout, the board that we designed, we have to extract the S parameters from it. So the S parameters are saved into a file that will represent the traces in the board. Then there is a backend simulator where these S parameters are put together to form a complete channel. Sometimes we put chip models there as well, and then run a separate simulator on that. And then it generates either new S parameters or time domain waveforms or some kind of waveforms that can be displayed as is, but often we post-process it to get more information out of it.
So I would like to point out, so S parameters is basically a file which describes your PCB, and then you feed this S parameter file between transceiver and receiver in your simulator, and then you run signal through your PCB, through the file which is describing your PCB, and then you can see the characteristics of the traces which are on your PCB.
Yes, and there is also post-processing. For example, when you can generate either another S parameter after stage 2, because in the stage 2, if you have, let's say, 2 boards talking through a backplane, there's 3 boards, there's 3 S parameter files, not 1. So you chain them together, you might generate 1 S parameter file describing the whole thing, or you might generate a waveform like an eye diagram. If it's a 1 S parameter, you might still want to process it. For example, generate differential mode S parameters from this original single-ended mode S parameters, because those are the differential mode ones are the ones that we have to compare against the standards. But it's the processing using equations or algorithms. Some simulator programs just allow all of this to happen inside, and you just click simulate and it will do step 1, step 2, step 3, all inside. But in more high-end systems, we use tools that are more sophisticated, and it requires the user to handle each stage separately.
So let's go back to what kind of tools, simulation software we can use. I see this is ADS, I think. Inside ADS.
This diagram comes from a tool called QUCS. It's a free tool, but ADS is similar. So in QUCS, maybe I'm not pronouncing well, and I will discuss this anyway. It's an open source program that can be downloaded. I created some templates for it that allows us to create a stage 2 model and stage 3 post-processing.
Oh, I didn't know this. I thought it's ADS because it looks like the schematic. It looks exactly like from the ADS.
Oh, so this here is from ADS.
Ah,
for
sure. Okay.
But this QCS works like ADS. I think that it's a ripoff of ADS.
Can we find website, because maybe people they would like to check what kind of software it is.
Which one?
The free simulator.
Okay. So the simulator itself might be not enough for you to do signal integrity analysis. So in order to do that, you would need to create a template. I spent many hours creating these templates. This is what a simulator looks like. You have to create a schematic, but it's not a schematic to turn into a board. It's a model schematic. So I can probably run the QUCS if it is willing to work. Okay, so anyway, in both ADS and QUCS, you have to create a template or use someone else's template. And that's what it looks like. That's the template I
Oh,
created. There's a bunch of equations in it. Some of them are even hidden. I think this one has dozens of equations I had to develop. You see, there's so many of them.
and if someone buys your book, they will get access also to these templates, or?
Yes, although you can download this from my website
Oh, okay.
right now.
So what kind of website do you have?
This is my website. It's
Mm-hmm.
called buenos.extra.hu. There is high-speed design calculators. There are these QC and Excel templates. So the one I was just showing is the SERDES channel template here.
Perfect.
Yeah.
Perfect. Let's go back to the slides. Okay, let's go up. So what are the next slides? Which one where we finished?
Okay. So we had this.
Yeah. So this
Interface.
one, low speed interfaces.
Yeah, they get a little more complicated on a motherboard than it is on a microcontroller board. And there are more of them as well, and more different types of them. For example, an SPI bus is used to load the BIOS into the chipset and then into the processor. For the SPI bus, we have a flash chip, and here I show ASIC, but for this case, it's a chipset. So instead of just connecting them directly, we use a multiplexer chip and a header, so we can turn the multiplexer to channel 1 and then program the flash chip from a header, because we have to design a motherboard to be manufacturable. You have to get the data into the flash chip, and if you just connect it to a CPU, there will be no way of programming it.
And sometimes I think they are even like two chips. Like one is the backup if something happened to the, or
Yes, and they can make it even more complicated with the backup. The selection between the backup and the main one can be done by the management controller, the microcontroller on the motherboard. This is used in servers, I think.
what other interfaces are there? So these are SPI.
Yes, there's a JTAG
JTAG.
interface. The desktop motherboard might just have a single header to a processor, and that's it. Not on embedded. If you have multiple processors, FPGAs, ASICs, you might have multiple devices. Then you create a JTAG chain where all the devices access to the same one header. And this diagram just shows that the I2C bus is, it seems like two nets in the schematic, but it can mean different things. Different levels of protocols can be used on it. A simple I2C to read a sensor might be just sending a byte or reading a byte. There's something called PM bus that defines a protocol to talk to smart devices. They require a transaction like this with 6 bytes to read something out of it.
I'm just curious. So how many pages this kind of how many schematic pages this kind of board may have? I know, but I would like you to say, because maybe sometimes I know sometimes people think like 10 pages, that's a very big schematic. So how many pages?
So depending on how dense you want the pages, yeah, I like to have large pages with a lot of stuff on it. In that case, you can finish a motherboard in like 30 pages, but most people have a smaller page size, and with that, you end up with 100 to 300 pages in a schematic for a motherboard.
Yeah, and I would like to point out very often the schematic is not only schematic itself, it also includes all these kind of block diagrams and power sequencing and all these things, many of the things what you already have here in these slides.
So it's a good practice to, so first when we start to design, we start with the top level I/O block diagram. Then we create the block diagrams for each subsystem, like power, clocking, thermal management, I2C buses, PCI buses, and several other things. And depending on how complex your board, you will have at least 2 other subsystem block diagrams. Well, for very complex designs, you might have 10 subsystem block diagrams.
Just block diagram. It's not even schematic. It's only block diagram.
Yes, it just explains the functionality. So it's a good practice to put those in the first few pages of the schematic. The very first page would probably have a table of contents. After that, block diagrams. You might have a power sequencing diagram or some port mapping tables. If in some complex designs, a chip might have lots of things connected to it, and you might want to provide a spreadsheet or a little table showing port 1 is connected to this, port 2 is connected to that, and that would take up a page, the schematic, and the actual schematic starts after that.
Yeah. So for example, I2C bus, there may be number of I2C devices, so we would like to maybe put their addresses for these devices, or why to create the block diagram for power distribution, because if there is like, I don't know, 30 power supplies, it's impossible to keep everything in head and drawing the schematic just from the head, because ideally you would like to know also what are the maximum currents, what are all the voltages, what are the maybe control signals for these individual power supplies. So it's very useful to actually create the block diagram and then draw the schematic based on the block diagram.
Yes, even on my own designs, I look at my block diagrams a lot because I can't remember it. I think the block diagrams act like an index in a database. So first look it up here, then go to the detail.
Yeah, exactly. Okay, so page number 8. What is on page number 8?
SERDES interfaces. Now these are, so there are low-speed interfaces and high-speed interfaces. The modern motherboard, we don't really have PCI buses and these kind of things anymore. So the 3 types of interfaces we have: the low-speed interfaces, the SERDES, and the memory interfaces. The memory is running around 3 or 4 gigahertz right now, and they're single-ended. There are SERDES interfaces that are several gigabits per second, and they are serialized, and they are more affected by signal integrity concerns and analyzed through S parameters. But that's the motherboard. The most common SERDES interface is the PCI Express. It goes to some of the sockets, as well as there is a special version of PCI Express used between a CPU and a salt bridge.
So SERDES interface is basically differential pair input buffer and output buffer or something like this, yeah?
There is a lot of logic that is implemented inside the chips. The serializer, deserializer, there is a clock data recovery because we don't provide a clock to go with the data. There might be a clock. It's called a reference clock, but that is not suitable to decode the data on the stream because it's not in phase. So the actual line clock is extracted from the data stream with some of this logic for the clock data recovery circuit inside the chip.
But between the chips itself, these are like only kind of differential pairs. That's it.
Yes, there is a receive and transmit differential pair, and typically there are multiple lanes in some interfaces. Other interfaces are single lanes. In a single lane, there is a RX and a TX differential pair. And then for PCI Express, they also get a reference clock, so they can run their internal logic.
And it's always like called SERDES, and you can configure them, or if it's like, it's always like interface specific, or?
In case of an Intel chipset, it's fixed. Some pins are dedicated for PCI Express, other pins are for Ethernet, and so on. For FPGAs, it's configurable which one to use for which. FPGAs provide a bunch of SERDES pins as well as generic I/O pins, and any of them can be used for any protocol.
And what about displays? Because I remember display interfaces very often on these chips, they were kind of universal, and we could configure what kind of interface we would like to use.
So Intel processors can provide a serial video output. I don't know about the latest chipsets, but some of the earlier chipsets provided a display port output, And if you wanted an HDMI on your motherboard instead of DisplayPort, then you need an HDMI level shifter.
Mm-hmm.
See,
So
this
there was
desktop
extra chip.
motherboard has it has an extra chip, HDMI level shifter. It just converts from one type to another. This is also SERDES interface. It doesn't have RX and TX. It's just one direction from here going out to the connector.
So basically, these SERDES interfaces, they can have, or basically the difference between different interfaces, maybe one of the differences is the voltage level. Yeah.
The voltage level in case of DisplayPort and HDMI, but for all others like Ethernet, PCI Express, it's kind of the same voltage level, about 1 volt peak to peak. And I don't remember adjusting the voltage level on the FPGA. Instead, the speed is adjusted and the protocol is adjusted. How the packets are encoded, that's different. So logic behind the SERDES is different.
Okay. And I also wanted to mention this because this is one of the most common interfaces on these very high-speed boards. On the server boards, everything goes through SERDES, all the high-speed Ethernet and everything. Yeah.
Yes, any high bandwidth connection that carries video or user data or something. In a server is usually located in a data center, but they don't just have one server. They might have 20,000 servers, and each of those handle thousands of users or maybe hundreds of users in the same time. Even though you're only downloading let's say a video, maybe 1 megabits per second, another 100 users do the same thing, or another 1,000 users do the same thing. It all aggregates through some of these interfaces like PCI Express or Ethernet. So they need to have a large bandwidth, and the way you achieve a high bandwidth is high-speed signals and several lanes of those.
Okay, what is on the next slide? Memory interface. We already talked about the memory interface.
Yeah.
Next. Power supplies. Oh, I remember once I asked what people think how much current standard processor, Intel i7 processor can take, or how much current it needs, the core. And they were like 10 amps, 20 amps. So can we talk a little bit about these currents?
So each processor, an FPGA or ASIC, have a core rail and several other rails. So they require usually like 5 different voltages, and they come from separate voltage regulators. The core rail is the highest current rail on these devices usually. Now,
How
desktop depends on what kind of application. On that laptop motherboard I showed you, it's probably like 10 amps, but in a desktop motherboard, it can be 100 amps, and the highest I've seen was 400 amps. And that is at 1 volt. And in order to deliver such high current, you have the multiple phases. Each have a phase controller and then the main voltage regulator controller. This creates 1 voltage rail. I think this is like eight phases, but I've seen 12 phases as well.
So what is important about delivering power to processors for these very high currents? Placing them close to the processor, I guess that's one of the things.
Yes, so we deliver power through the power plane. I had a slide about it. For a slower power processor, you might deliver power to a narrow power plane like this that just connects to the core. But if you have more current delivered, then you have to make the plane envelope the processor, and then the current flows in all directions. You might need multiple layers provided for the same rail. So the important thing is that the voltage here is generated by voltage regulator, but the voltage here seen by the processor might be lower than that because voltage drop through the plane. If the plane has a resistance to it, even this white plane might have milliohm to it. It doesn't seem much, but if you have to deliver 100 amps, then it might drop a lot of voltage. So there are several techniques developed to handle this. One is to have thicker copper, have this enveloping power plane, have multiple layers of power planes. And there's one thing that some voltage regulators have, which is remote voltage sense. There's a signal coming from the controller, the signal trace connected to the plane here. But the layout tool might want to just eliminate the trace and just connect to the plane here. we have to not let the layout do that. In most cases, the processor has separate pins, so they internally connected their power pin to the feedback pin inside the package or inside the processor to allow us having a separate net that would be handled by the layout tool differently.
So directly we have access
here.
to measure the voltage directly on the silicon, and we tell this voltage to the regulator, and regulator can actually adjust the regulator will know the exact voltage on the silicon this way.
Yes, because what is important is for the silicon to have the right voltage, not that the regulator has the right voltage. So because of there will be voltage drop, let's say you need 1.00 volt here, then in order to maintain that here, the voltage regulator might have to pump out 1.05 volts or something.
And also, I think this is one of the things, again, what is a little bit more complicated comparing to other kind of boards. On x86, very often the core voltage can be changed. So there are some protocols or ways how processor is telling the regulator or something else is telling regulator what should be the voltage on the core, and they can change it based on, I don't know, what it is doing or something.
Yes, I think so. x86 processors have this voltage adjusting protocol that also makes x86 board more complex than an FPGA board, for example. Most FPGAs are happy just running on a fixed voltage level. The laptop processors like to adjust the voltage more than desktop processors do. I think that's what they made it for. If the voltage increases, then the processor can be run at a higher clock rate as well. So some of these Intel processors, when you start running some application like a game or some simulation, then they realize that there is more performance needed, so they bump up the processor clock speed and the voltage at the same time.
Do you have something? Can we go back to the regulator page? What was there about because you had different kind of regulators there on the pictures?
Yes, in these pictures, so depending on what rail, on which design, as well as the designer's preference, sometimes they use a module instead of a chip down. So there are two options. You design your chips and all the components down on your motherboard, or you just design a module that might have maybe 16 pins and a big cube, everything in it. I only use a module sometimes for like low current rails, but I've seen some people use it for a core rail as well. I think it has a lot of inductance to it. So I wouldn't use it for a core rail. Another arrangement when you have a single chip, but you have MOSFET chips on the board, plus all the passives. Now, this old style, I don't think anyone uses it anymore when you have one MOSFET and a diode and a controller chip. What is common for smaller rails is this arrangement when a controller circuit and a MOSFET are in one chip. So basically, for a designer, they design that one chip plus the passive inductors and capacitors. But for the core rails, it's this one chip splits into multiple chips: the phase chip or power stage chips, several of those, and a controller chip. And there's a digital interface between them.
So these are like multiple power supplies of same voltage connected in parallel, so they can deliver much higher current.
Yes, and they are controlled by one controller chip.
So there, I have two questions. So first one is, do we need to simulate this? And the second one, do we need to do some kind of measurements for this?
Yes, so in my case, I rely on power supply engineers. So when you design a complex hardware, it's not a one person in a garage, but rather a team, and an extra team member is a power supply engineer. So I rely on them to simulate the power supply circuits that are dependent on the load, these component selections, what frequency we are running it at. This happens during or before the schematic design. But once you get a prototype, I always want the power supply to be tested for performance. I think I had a slide, some image, this image here. This is a 3D image of a fake board that I created in QUCS, and I mark it up with what is connected to it. So we make a board that's called a power board, where the CPU is not on it, not soldered on, CPU or FPGA or whatever, but everything else is on it. Power sequencer, voltage regulators. And we do something called the load testing. There's a load tester that you solder down, and then this will create a step load. It will just draw current out of the voltage regulator and then changes to different amount. For example, it draws 20 amps, then it starts suddenly drawing 80 amps, and then back down to 20 again. And then we solder down another cable or just probe it by hand for an oscilloscope. And that will show how the voltage changes when the load current changes. So that is used to see whether the voltage stays within a range that we expected. If not, then the power supply engineer would have to adjust some of the components. For example, replace capacitors, the resistors here, run the controller, and then measure again until we get a satisfactory small amount of voltage fluctuation. That's one test that we like to do. Another test is called a body plot that power supply engineers do, which is to measure the control loop frequency response.
On the page 24, I think you have a picture of the
24.
Yeah.
Yes. So this body 100 device is used for two different things. One is to measure this body plot by power supply engineers. The other thing this can be used for is to measure the frequency domain impedance profile of the power rail, the PDN impedance. So I usually do that measurement myself, and I let the body plot measured by the power supply engineer.
And I have done a couple of videos, or at least one video, where we did some measurements with this, and we also show how it can be useful. So if someone would like to see it, then I will put link somewhere. But the main point is, for example, to see if there are, if we can deliver the, we would like to see the impedance profile, because there may be some frequencies where this impedance could be too high, for example, and then it could cause problems. Correct? That's, for example.
Yes. The impedance peaks in general can cause problems, as well as in general I think I have another slide somewhere. This is how an impedance profile looks like. It can have peaks, can have any kind of shape, and usually there's a target impedance line that we calculate, and all the impedance has to stay below it. This line is not on this picture right now, but if we find that the impedance profile pokes through the target impedance line, then we might have to do some adjustments. Now, what we can adjust on a prototype is typically the voltage regulator's control loop can be adjusted, that we have effect on the lower frequencies. We might have to add more capacitors, solder them on the prototype, and then that can change as well, or replace them to different values through a rework. So on a prototype, we'll have to make alterations, component changes by hand with a solder iron under a microscope. And once we made those alterations, we have to write down all the alterations we made, and then update the schematic and the layout, and respin the board design. So what will happen if the impedance profile pokes through the target impedance at a few locations, it might boot up in the lab, but I wouldn't ship it to the customers like that, because the customers will run different applications on it, and sometimes it will just crash, blue screen, or shut down. So it's a reliability issue. If the impedance is so bad that it might not power up ever, but in most cases, it's called power integrity and the signal integrity. Both of them have this relation to reliability. It might work for a few minutes or something, but it's not good enough for a product. So it's not a hobby. We're not talking about hobby projects. We're talking about designing a product that we ship to customers. It has to work all the time properly.
Yeah. I remember when I was starting with hardware design, I was like, oh, this board, it works. It only reset itself once a week. And then when I was designing for longer, I was like, once a week, it means it's bad design. Something is wrong.
Yes, even for consumer electronics, it would be very annoying to the users, and they write reviews and so on. For the other industrial and the data center, these have to be more reliable because in case of an industrial design, a customer might be a billion-dollar company. You will say that, okay, we wanted to order $200 million worth of products from your company, but now we are not.
Yeah.
So that's pretty bad.
I remember real world example. There was a company which was using a board, and when this board freezed, they had to like clean all the machines, and it cost a lot of money and it took a lot of time. So even if it freezes once in 2 weeks, it was like big problem for this company.
Yes, if the electronics works in an airplane or a train or even in a car, it cannot reset.
Yeah.
Right? If your car resets, then you must probably die.
Exactly. So that's one of the reasons why if it looks like everything is working okay, you still have to do a lot of measurements. Yeah.
Yes, I do this power integrity measurement, PDN impedance. I ask the power supply engineer to do load testing or body plot testing. Some of the signals are measured, although most signals are not really measurable, especially the high-speed signals. But what is measurable and accurate is called an on-die eye capture, and it looks like this. Because this is captured by the actual chip that's receiving the signal, and the signal only has to be good at the chip that's receiving it. If you connect an oscilloscope to it, it's a totally different arrangement. So whether it's good at an oscilloscope, whether it's bad at the oscilloscope, it's not very consequential to whether the product is reliable or not.
So you can extract this by some software directly from the chip, from the, well, what is it, equalize, how it go or something?
Eye diagram, I don't know. On-die eye capture, that's what we call it. Some chips support it. I'm not sure whether Intel processors support it. All the FPGAs support it. Some of the ASICs support it.
I didn't know this. That I learned something new today. I had no idea there is something like this.
Well, there are a lot of people still try to measure signals with oscilloscopes. At the low speeds, like SPI bus, it's still proper to measure it. We always do it, part of the design verification. But for most high-speed signals, trying to tap on with a probe, it alters the signal. So we don't know whether the signal got worse or got better by probing it.
Yes, exactly. It's something what I've seen a lot. Some people, they ask me like how to measure memories. It's possible. I've done some videos about how to measure memories, but normally I remember I have never really measured memories. What we did like extended testing for like long run tests and then environmental chamber tests and all these kind of tests.
Functional tests.
Yeah,
instead of
functional test. Yeah, exactly.
There is one measurement that can be done in a memory, and it is done automatically by the BIOS when the computer turns on, and that's called the read leveling calibration. It's done in order to set the controller up automatically, but this process produces some data that you can extract. For example, if your BIOS engineer changes something in the BIOS to print this out in a serial port, then you can observe how it went. And it is like an eye diagram, but instead of two-dimensional, it's just one-dimensional eye diagram. So it shows like 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 0, 0. So the ones in the middle show the width of the eye. If it's small, then the design is not so good. If it's wider, then it is good.
I can explain a little bit more about this because it's very similar for ARM. I've designed many ARM boards, and we had to do this memory calibration. So basically what it is doing, it is adding delay to data lines, and this 0, 0, 1, 1, 1, it means doesn't work, and it started working, it's working, and it doesn't work, So basically based on this width and where exactly it is placed, it's possible actually to find out when it is going to work and how good.
Yes, it's a very genius idea that they had, and it's standard for starting with DDR3, DDR4 memories.
Yeah. We didn't talk about debugging. So how do you debug this kind of boards?
So there is a prototype debugging. So first we design a motherboard, then we get the prototype made. So the engineer has to debug it. Usually there are design errors on it, a few, and we have to find that. And also there is new firmware on it that we have to program into it that was never tested before. So we always have this dilemma of when something doesn't work, it's the
It's
firmware
software
or
or hardware
hardware. So yeah,
or the board.
or manufacturing, yes,
Manufacture, yeah. Is it the
sometimes.
schematic? Is in the PCB? It is the manufacturing? It is the component, or it's the software?
Yeah, so this debugging is heuristic usually, which means you have to have intuition and ideas to find, oh, maybe this is causing it. Another thing that I do in prototype testing is experimentation. So, for example, if something doesn't work, but I don't know why it doesn't work, I can guess why it doesn't work. Okay, so if it's caused by X, then I could fix it by doing this. So let's apply that change, or change a resistor or something. Then I apply a rework that looks like this, and then test again. If it works, then okay, it was caused by X because this change fixed it. If it didn't, then I have to come up with another theory, then do a different alteration and run again a test. And typically, most experiments don't work. That's why you have to be ready to have several ideas for the same problem. Most bugs can be resolved in 1 or 2 days. There are a few bugs that might take 1 or 2 months to resolve, but those are typically caused by something in the data sheet that was ambiguous and we misunderstood. We looked at it again and we misunderstood it again the same way.
Or it was
Yes,
not even in
someone,
datasheet?
yes, or we asked someone in our team to look at it. They looked at it, they misunderstood the same way because sometimes they write something in the data sheet that is only the person who wrote it understands it. Everyone else will have a different understanding of it. So this happens.
I had also when we are talking about this, I remember once I had problem with they fitted different capacitor values. That was very hard to find. I had to actually start desoldering components and measure them one by one because I was like, I tested everything and I was like, it has to be component. So this was difficult one. And the other difficult ones are which are silicon related and manufacturer they don't want to share this problem. So you actually have to tell them like, I tested this. It looks like the problem is in silicon, and then they will tell you, yes, it's problem in silicon. But
This happened to me as well. You have to point out exactly in this register we set this bit, then
yeah,
it worked. Why? And then, well, we know that problem.
yeah,
Okay, and that's after 2 months.
exactly. And then there are kind of silly mistakes when if I would read errata, I would find out, oh, okay, that's like standard issue.
But most of the problems are actually in our design. Let's say maybe 90% of them. So we can never know upfront whether it's a chip problem or our problem, but there are many of our problems that has to be fixed. And again, we apply these reworks to alter the design. Instead of respinning the door, several changes can be done. For example, we connected a signal to this pin, but we have to connect to the other pin. So instead of respinning the board and spending tens of thousands of dollars on it, you might just cut the trace and wire it to the other pin and then see whether it works. Or a missing pull-up resistor or something like that.
You know,
Yeah.
this is again something what I learned by experience. Sometimes people ask me, "Why do you connect this pin? You are not using it." Like, oh yeah, I'm not using it, but maybe if there is problem and I need to access this pin, then I need to take it out.
Yes, there is another thing that we do in complex hardware design. It might not be needed on a microcontroller board, which is to design it in a way that we can alter it later. For example, have a do not populate pull up that is the footprint is there, but I don't think it's needed. I'm not sure because the data sheet is ambiguous. So on a prototype, when I test it, then oh, I should have had a pull up, but I have the footprint. I just put it on. It's a lot easier to put on an existing footprint.
Yeah,
I need to cut traces and go somehow under the chip and wire it.
exactly. Exactly. That's exactly what I'm talking about. Okay, what else we have? Because we only have maybe like, I don't know, 20 minutes. So what other pictures we have here?
PCB materials, maybe.
Okay, so what is there difference between PCB materials? Do we need to consider something special when we are designing these very high speed, big, large boards comparing to small microcontroller or small processor boards?
Yes, so starting, if you have any 8 gigabit or faster signals, then signal integrity and the PCB materials become very important. The stack-up has to be designed even for lower speed boards. There's a dielectric materials. They are defined by something called a glass style. That's a 4-digit number. If you have a 1 gig board or a 5 gig board, you might just let someone else define it. And that was pretty common at large companies. But for 8 gig, you definitely want to know which glass style we use because the signal will have different quality depending on that. And then starting around 25 gigabit or 56 gigabit, the losses have become the insertion loss, the attenuation of the signal become very strong, and we have to deal with that. Now, I wrote about this in my book. It's not very well known how to deal with the insertion loss in PCB manufacturing. Basically, you have to know which PCB fabricator can manufacture how much insertion loss. For example, one vendor, if you make your PCB, you have 10 dB loss on your traces. If you don't made by another vendor, it will be 7 dB. So that difference has to be characterized. Now, for that, you might need a signal integrity engineer, or you might be the signal integrity engineer yourself, but at a large company, you might have a signal integrity team who will characterize the vendors for you and tell you that if you have 56 gig signals and your loss budget demands certain amount of loss, then you can use these vendors. And they do it by making SI test boards, or there are also contractor companies like Wild River Technologies who make these SI test boards for you, design it for you, send it to the fab vendor that you want to work with, and they will measure it for you, characterize the vendor for you. So it gets very complicated. It starts separating on 25. Most desktop motherboards don't have 25 signals or 56 gig signals on them. They go up to about 16 gig right now with the PCIe Gen 4.
What was the company name? Can we find it? Because maybe I could
Oh,
contact them and maybe make video with them because it could be
yeah,
interesting.
I wanted to suggest that you talk to Wild River Technologies, Al Neves, Alfred Neves. I
Can
can
you
send you
find
the
them?
con.
Can you find
I,
them?
I, I, can, I can find it on the internet. Uh, let's see this.
Okay. Okay. I may try to contact them and let's see if we could make video together because this could be interesting.
Yeah, so they have designed their test boards like this, and they measure it for you. And this the purpose of measuring it is to characterize a PCB fabricator or a material that you want to use.
Perfect. Perfect. Thank you. Okay. What is on the
What
next
else?
slide?
So did I mention this before, the floor planning?
No, we did not.
So whenever you design a complex board, you have to create a floor plan analysis. And some people think that this is just the layout will fall in as it may, and we don't care about it. But for high-speed and complex boards, I do the floor plan as the very first thing in a project. Once I have a block diagram, the main IO block diagram, I don't even wait for the subsystems block diagrams to complete. On the main block diagram, I can create this floor plan. Basically, take pictures of existing boards, or download pictures from the internet, scale them in an image editor, and then cut out these little pieces that represent components or subcircuits, and then try to fit them in according to the block diagram of my design. So there are several purposes of this. One, we have to see whether all these features will fit in a given board size that we wanted to do. And often there are standard form factors and the board size is given, and you cannot just grow it by another inch. So you have to see whether those features fit in it. And then you will mark up the main connections on it with these, it's not shown here. You will mark them up like this is connected here, maybe another chip is connected here. And then you would try to assess how long those traces are. And these are important for the higher speed traces, like 25 gig or faster, because you have to do a loss budget calculation.
Mm-hmm.
For example, for 10 gig Ethernet, you would have a 30 decibel loss budget. And if you have 10-inch traces, then you can have 3 dB per inch. If you have 20-inch traces, you can only have 1.5 dB per inch.
Mm-hmm.
Then you have to make sure that your manufacturer or fabricator can deliver that dB per inch loss.
This is a very good tip because I think everyone should notice it is in scale. So you have these rulers there. So even the processor is in the scale, memories are in the scale. So basically, when during the schematic design, you can actually see if everything is going to fit. You don't have to wait until the placement.
Yes, exactly. And it's very important to find out the loss, whether you will meet your loss budget from the trace length or not, or whether you fit all the stuff in the form factor. For example, you decided that you want 3 FPGAs, then it seems like a good idea. Well, why not? But it has to be in a 5 by 5 inch board. Okay, then try to packing it, only 2 fits. Now what do we do? Use a different FPGA? Okay, if you have to use different FPGA, then you have to know it up front. You cannot just go back to the drawing board
Yeah.
when you are already preparing the layout. Oh, we cannot use a Vertex, we can use a Spartan 7 instead. If it meets your application, you can do that. But then you have to redesign the schematic, the block diagrams, and everything. So it's better to know this upfront whether it fits or not.
Okay. What is on this left side? So these are the losses, or what is it?
So this is how loss budget works when you
Mm-hmm.
have 3 boards. So the loss budget is how much the signal can attenuate, and that's defined by the standards like IEEE or PCI SIG. And this only matters from a chip to a chip. If you have a backplane, then there are 3 boards, and the first chip is on one board, the next chip is on another board. So the signal travels through 3 boards. The losses related to the trace lengths and the fabricator from all the 3 boards have to be added up, and that has to be below what the standard says. For
Mm-hmm.
example, backplane Ethernet is 30 dB maximum.
Mm-hmm. So
All these
basically, based on these losses, you can calculate what is the maximum length of the trace what you can use on your PCB.
Yeah. So you calculate the maximum length, and then from the floor plan, you check how long the length will be.
Mm-hmm.
And if that length is more than the maximum length, then you have to change something.
Yeah.
Change the form factor, move the components, or change it to a different fabricator.
I would like to mention when I was designing these x86 boards, then I was super careful about the schematic and layout and everything, because if there was something wrong on the board, it could take so much time to actually find a mistake, because you could power it up and nothing happened, and now you have to like find out why it even doesn't power up, why it doesn't power up. So you can spend so much time trying to debug this kind of complicated board that I rather spend 1 week checking the schematic and be sure everything is connected properly than trying to debug something which is like super hard to debug.
Yes, we have to make sure, but there's always a few that escapes or checking. That's why we have something called a peer review, when other hardware engineers at the company will review your schematic, and usually they consider it as an important work for them to review someone's schematic. It's important for the company especially. So they review your work, then you review their work in their project.
Mm-hmm. So, and what is your experience with debugging? Because we had, I remember we had also JTAG for debugging the Intel processors, but it was super hard to use. I connected it a couple of times and played with it a little bit. I uploaded maybe some firmware, something, but I never really used it for debugging because it was too complicated.
So one of the most important things for debugging the prototype board is to debug the power management subsystem,
Yeah.
the power sequencer. So you need to, typically we have like 30 voltage regulators on a motherboard, and one might be tuned with the resistors and capacitors in a way that it's unstable and cannot turn on. We don't know which one. So we have to have a power sequencer to be put in a mode where every rail is forced on, for example, or there's another mode that we can use. We have to have debug modes for the power sequencer, either force everything on or let the sequence go, but when one rail fails, then it just wait there.
Mm-hmm.
The shipping product would not likely to have the shipping product. If it runs into a bad voltage rail, then it will just shut down everything and all the evidence disappears. So you have to put it in a debug mode. For example, a GPIO going to the sequencer from a jumper. If you put the jumper on, then the sequencer knows that it's in the debug mode and it has to keep everything up. That's one mode. The other thing is the sequencer chips typically have a JTAG interface, and you can create a timing diagram over JTAG to see turning on this rail, the next rail, the next rail. Oh, the way you see it in this JTAG time diagram is power enable goes up. The power has to go up after it. For let's say the first 5 rails, this happens. Rail number 6, power enable goes up. Power good never goes up. You know that rail didn't turn on. Then you have to get a power supply engineer to debug that rail.
Mm-hmm.
This JTAG thing works through something called I call it live system boundary scan. There's a software that you can buy called Top JTAG Probe. It's really good. It's just $100, and I always use it on prototyping.
Mm-hmm.
If the power
Which one it is? Can we find it? Maybe it can be
Yes.
useful also for other people.
It's called Top JTAG Probe. Yeah, this works.
Yeah.
Interesting. TopJTAG.com. You can program flash devices through this software, but it's a different software. I use the TopJTAG Probe.
Mm-hmm.
And it looks like this. You have to get the BSDF file of the JTAG devices from the chip vendor, and you have to define some sign, depending on what device you use. For an FPGA, you have to load a file that has the signal names that you have. For example, rail 1 enable, rail 1 power good, and so on. And then try to turn on your system and then press run, and then it will create this timing
This is cool.
diagram.
I didn't know something like this exists.
Now, this requires a JTAG-capable power sequencer. Some motherboards have this embedded controller that may or may not have JTAG, but in most embedded designs, we use a small FPGA for power sequencer, and this works very well with that.
Mm-hmm. Okay. And then, so you switch on all the powers and it's not booting up. So what do you do?
Okay, so in x86, there's a BIOS, obviously. So we have to ask the BIOS engineer to put the BIOS into verbose mode. Every little thing that it does, it will put out a message to the serial port. So very first thing you would do is connect the serial port to your computer. You need a USB serial adapter, and then see whether anything comes up on it. If nothing comes up on it, then either the serial port circuit doesn't work, or the processor didn't start booting at all.
I would like to point out this would be special serial port, for example, from the microcontroller, which is reading the BIOS and doing the control chip. This one can send some serial messages, or it would be that's what we used before, or it would be standard. What we also used was the how is it called? There is standard interface on LPC for LPC. Yeah, you can send some messages and read some BIOS or postcodes.
Yes. So you would have a postcode card
Yeah.
connected to the chipset through the LPC bus, but it just displays a code that is useful. When you turn it on, it should start counting numbers on it. And if it fails halfway in the boot up, it will stop at a certain number. You can look it up from the BIOS vendor what that number means. If no numbers go at all, then it didn't start booting at all. You can also probe the SPI bus where the flash chip is. Were there any transactions?
Yeah.
If there wasn't, then it's some basic electrical problem. Maybe the chipset didn't get a power good signal. Maybe some voltages are not turned on. Maybe the resets are not good. Sometimes the Intel chipset wants the power good and reset applied a certain timing. Like but the power is on. 100 milliseconds later, you have to apply this. If it's 200, it's not like it. If it's 80 milliseconds, it doesn't like it. So the very early stage when nothing works, that's the hardest part of debugging because you have to guess a lot and experiment a lot. But later, as you progress a little bit more, if you get your motherboard boot up halfway, it's even better because then some of the diagnostics will
Yeah.
already work then,
Yeah.
like the postcode or the serial console messages.
Yeah. Yeah. Okay. What is on the next slide? We talk about the next one.
I think we discussed this.
A little bit. We didn't talk. You use active probes. I think you mentioned to me before the call.
So low-speed signals can be measured with an oscilloscope. With a, let's say, a 20 megahertz signal can be measured with a basic probe. If you want to measure something like it depends on what you want to measure it for. If you want to see whether it's toggling, a cheap probe is good in a 20 megahertz bus or 50 megahertz bus. If you want to see the signal integrity on it, you might need an active probe. And for high-speed signals, you can only probe it with an active probe. And for SERDES signals, I would use this kind of soldered down tip with an active probe head. If you measure a SERDES signal like a PCI Express, then all you can do really is to see whether there's something on it or it's just flat. Some people try to use it for signal quality measurement, but I wouldn't use this for signal quality measurement. At least not for a pass fail or like see whether the meet the standard. What I use it for is see whether it's toggling or not. If you can go a little further with this, for example, if you measure a PCI Express, let's say you have a PCI Express device and a processor, and the processor doesn't detect the device. You can measure with this both the TX and the RX signals, and you would find maybe that there are signals going up for like a few milliseconds in one direction, but no signals going in the other direction. So then you would know that the device is sending the signal that's not toggling. That's the bad one. The other one that sends the signal is a good one. You know which device is not working.
But not really like measuring voltage levels or quality of the signal or something, because just connecting the probe will influence the signal itself, and also the signal, because there are all these equalizers or I forgot how it's called. It's not even the signal what the other chip may see.
Yes, usually the probing makes the signal worse.
Yeah.
In some cases, it might make it better. So that's why it is not really good for a pass-fail testing.
Okay.
The only thing I use for pass-fail testing is on-die eye capture.
So if someone is really interested to learn a little bit more about these complicated boards, there is a project called Open Compute Project. I think it's on last slide or somewhere. No, you have there the Open Compute Server board.
Yes, this link here.
Yeah.
There are server boards, network boards, and this AI accelerator. There was one project there that was an AI accelerator. It was a big flat chassis, a big board with PCI Express switches, and they plug in these AI cards, either a GPU on it or an AI ASIC on it. 8 of those are plugged into the big baseboard, and that acts as an AI accelerator. They connect it to servers through cable.
And on page 38, I think, can you have a look? You have picture from these. Yeah. This is, for example.
Server. This is just a server. It's not
but it's from the OCP, Open Compute Project.
Open Compute.
So basically, if someone goes to this website, they can download even like layout files, schematic files. Again, I've done video series about talking and going through one of these schematics and layouts, which was from this Open Compute Project. Huge boards, anyone can have a look how the layout looks for this.
Yeah, it's a good exercise to look up how the power management subsystem was implemented, how the management was implemented,
layout,
how the logic, and how the layout was implemented, how the high-speed signal, how the memory or the power planes were implemented, and they can be used as an example. This Open Compute is really good because before they came along, all the complex designs were company secrets, and people who were trying to get into this field, the only chance for ever seeing one was to get a job first, and then there they could see it.
Now your book,
Yes.
So go on the last page. Yeah.
So this is my book. This is available on Amazon. I don't know where it can be seen. I can see my own
Yeah. I
video.
can see it.
So this is about designing complex hardware. And as we discussed at the first slide, with the complexity, this is not really for hobbyists. This is for people who want to work in corporate hardware teams, companies who design serious hardware. So it's not for microcontroller boards. I assume that someone who starts reading this already knows how to design a microcontroller board or even an ARM processor board and knows what a schematic is and so on. And then building on that knowledge, we can learn how to design these more complex ones like a motherboard or even these even larger boards.
And I think you have it. Can we show the link on Amazon? So if someone is interested to buy your book.
Okay, so just type in complex digital hardware design and my name in a search, and then you can easily find it. So I saw that on the market, there wasn't really a book like this. That was one of the motivations. I read many technical books, but none of them really explain this. I had to learn it myself in the job, the several jobs I had. And most books on the market explain microcontroller boards. So it's good to read that first and then read mine.
And also what I found interesting about your book is there are many very like focused books, but your is like very wide and covers a lot of things, like whole process of designing this kind of board. It's not only about designing power supply, but it covers whole design. That's what I found very useful. Yeah. Okay. Thank you very much, Istvan. I really hope people will also have a look on this website and check your book. And thank you very much for helping me to create this video. Very useful information. I really hope it answered questions to many people. The questions what I keep receiving a lot, like how to design x86 motherboards. So thank you very much for this, Istvan.
Thank you for the opportunity.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedEval online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.